Ooh.
Good morning, ladies and gentlemen. We are reviewing for the quiz tomorrow. Let's do it. Okay. An electric charge, symbolized by original Q sub original sub zero, produces a field around it where forces are exerted.
Yep, that's the how can forces be exerted through empty space? That's a very difficult problem for science, has been, not anymore, since we have field theory that explains it.
Here's our original charge in both cases, right?
Yep.
And it produces a field either outward or inward, and you called it like spokes on a bicycle.
Yep.
Right? Okay, so the only way we know an electric field exists is because it exerts a force on a positive test charge.
And I just realized I should have made that force red, because that force is it exerts a force on a positive test charge. Yeah.
A zombie head. And we would see, arrows going either in or out depending on what the charge of this guy is.
Yeah.
Okay. The intensity of the field, the electric field E, depends on the size of the test charge, the originating charge,
Yeah.
and the distance from it.
Yep.
Right? So that means like how far
Yep.
how far this is from it, right? Okay. Okay, so here's our equation. The electric field equals the force of the electric field over the test charge. The ratio of the force on the test charge to the quantity of charge on the test charge defines E.
Yeah, so this is a definition of the measured electric field. And the force that's being measured is the force that the test charge feels.
Measured electric field.
Yeah.
Okay, yeah, I like that you put that in there.
Yeah.
Because there's another one, right?
Right.
We'll stick with this one.
And the amount of force that is felt at a particular point in space depends on how big or small the test charge is. Smaller charge, less force; bigger charge, more force. So it's a ratio that's important, because the electric field at a point in space is.
Okay, fields from two charges interact to exert forces at a distance.
Yep, it's the fields that are interacting.
Okay, so the field of this one and the field of this one.
They interact, yep.
Okay.
Just like we saw with the bar magnets.
Yeah. The direction of the electric field is defined as the direction of the force on a positive test charge, okay?
Yep.
So we can look here. If it says the electric field from an isolated positive charge, so this is our test charge, that's this guy right here, okay? And when I bring in my test charge here, this is a positive, right?
Yep.
So as I bring it in, this is gonna be repulsion, and if you remember from the video, those arrows extend out like this, right? And the closer I get, the bigger you get, the further I get, the smaller they get.
That's right.
Okay, and from this one, the electrical field from an isolated negative charge, so now our originating charge is negative, this is always positive, and now we've got attraction.
Opposites attract.
Right? Okay. Opposite charges attract, right?
It's the fields that are interacting,
And
that's
the
right.
fields, and you see it's kind of like their hands are reaching over and the fingers are pulling each other toward. Like
Yep,
that.
the charges aren't touching each other. That force is exerted by the field that's around them.
And then like charges repel, right? So their fields are like, ugh.
You're so repulsive, get away from me.
Yeah, so gross. Okay, Coulomb's law predicts the force between the originating charge and the test charge.
Yep. Notice we've been hitting this every day, boys and girls.
Yeah,
Should look familiar.
You guys know this. If the electric field is the force divided by the test charge, and we know that you can find the force by using this equation.
Coulomb's law.
Yeah, Coulomb's law. Wouldn't the electric field be this over this, or we just take that equation and we put it up there?
Yeah, we simplified this yesterday. Can you do it again?
Can you do it again? What does it look like?
Well, I think it's on the next slide.
is it on the next
Yeah,
slide?
it's on the next slide.
Oh, thank you. Oh. Okay. Oh, there it is. There it is. Okay. So we've got two equations when we're talking about the electric field. The field is this. Okay. The
Yep.
field is,
Yeah.
and we've got the electric field, and we've got the our electrical constant. And in this one, we're looking at the originating charge and the distance.
Yeah, it's the originating charge that has the electric field around it. Whether you have a test charge to measure it or not, the field is there.
The field is, yeah.
Yeah,
good.
you got a bar magnet sitting on a table. There's a magnetic field around it, whether you can tell it or not.
That's a good way to think about it.
Yep.
Okay, so the measured field, the measure is the test charge, right?
Yeah.
Because you're adding in something to help measure it. And we just got the force divided by the test charge.
Yep, and we've been playing with this.
Yeah, okay, so those are our two options. Write them down if you don't have them written down. Okay.
Boom, boom, boom.
Now, let's go ahead and do a practice problem here. So what is the intensity of the electric field? Okay, so you want to know what the electric field is. 0.25 meters away from a charge of
Negative 2.50 times 10 to the negative 9. Well, meters are the units of what?
distance,
Coulombs are the units of what?
charge.
So we've got distance and charge. We want to find the intensity of the electric field. Which equation do we use?
Okay, so we have two options. I'm going to go ahead and go for this option, right?
Yep.
Because I've got those two. Now the other one
Square
is
the
just
distance.
force and square the distance. Thank you, sir. Don't forget to square the distance. Okay, all right, so 9 times 10 to the 9 Newton meters squared over Coulomb squared times this, negative 2.5 times 10 to the negative 9th coulombs, and I divide it by 0.25 meters squared. Oh, I was just thinking about, don't forget to grab that. Okay, thank you. All right, so we've got no answer. 9 times 10 to the 9th times a negative 2.5 times 10 to the negative 9th. Divide that by 0.25, I'm gonna square it. And I get negative 360. What are my units? Okay, negative 360. If I forget my units, let's see, I've got a coulomb here.
Meter squared.
Oh,
Cancels meter squared, yeah.
yeah, meter squared is, Newton. Coulomb. Okay, that makes sense, right? Because because this is also force over the test charge.
Yep.
Right? Okay,
Units of the
Newton over
electric
Coulomb.
field are newtons per coulomb.
Yeah, okay.
All right, I think that's about all of this we need to do. You should know it by now.
Okay, so for homework, you're going to do page 502, and you're going to do, that's right here. Oh, I guess it goes on to 503 too, sorry.
Yeah.
2 and 3, and then numbers 23 and 25. And then also, I encourage you guys to look back over your Lost in Space handout.
Yep.
Everything you need to know is on, well, we've already talked about it all, but is on the Lost in Space, practice problems, and this review.
Yeah, and any question, anything you don't understand on that, you should get that cleared up in class today before we take the quiz tomorrow. Sweet.